All right, welcome everyone. Welcome back to class number 7. You guys can hear me all okay, right?
Yeah.
All right. And as always, if possible, let's turn on our cameras so I can see the faces. Let me see if I can focus this. All right, let's see. While you guys are trickling in, I will struggle with technology as always. Someone's playing in the background. Huh? Is that clear enough for you guys? Can you guys see it?
Yeah.
I'm a B.
See, I learned my lesson. Rather than fumbling through the technology later, I might as well fumble through it now while people are joining. All right, let's see.
Fuck. All right.
It's similar to last time. Hey.
I'm gonna cut it. Oh shit! There's all my losses. Look at that.
Oh, because you're trading your stocks.
Nah, bro. Those are there.
Welcome, everyone. We're waiting for a couple more people to come in, but while we're here, let's turn on our cameras and get ready to have a good time.
Shut the fuck.
That's good enough. If at any point the screen is too blurry, just yell at me and I'll fix it.
Yeah, or else I'll show you my balls.
It's too blurry for me. I'm really just that my camera sucks.
Is it blurry for everyone too?
No.
Then it's something.
Don't mind the algebra, kids.
Never mind, it's good now.
It usually takes a little bit to warm up. All right, it is 8:33. I guess I'll get started. How's everyone doing today? Let's see, we have 1, 2, 3, 4, 5, 6, 7. That's close enough. All right, well, I'm glad to have you guys back this week. This week is my last week. Is that hard to believe? One more week and then you guys don't see me again. So if you love me, I'm sorry. If you hate me, that's great. You only have to sit through 2 more lessons of this. All right, so, well, I'm just focusing the camera here. Anybody have any questions at all before I get started? Let's try to keep the music down, Ernie. All right, so I'd like to start by going over a homework problem first. All right, this was from last time. Last class's lesson was kind of intense, right? Today's lesson hopefully won't be too bad. All right, so I'm looking at the question 19 on the back page of the homework, which talks about codeine. This is what codeine looks like. Does anybody know what codeine is? Has anybody here ever been to Hartford
It's
or
that
anything?
drug, right? Yo, it's that drug.
Yeah, codeine
It's the opioid, right?
Yes, codeine is a narcotic. It is a weak base, and it looks just like this. This is the chemical formula for codeine, and codeine is used for pain relief. And Ernie, codeine is used for
That was
pain
an
relief.
accident.
Okay, I'm gonna... Oh, oops, what did I just click? Oh, God, what did I just... Oh, oops. All right, so anyway, codeine is a pain reliever. It is a weak base. And what happens is, a fun fact about codeine, since it's a weak base, it gets absorbed into the body through the small intestine, which is why when you take codeine, it can cause constipation. That's one of the reasons, because it's absorbed through the small intestine and through the colon. All right, but anyway, our question in chemistry is, we have a 0.05 molar solution of codeine. What is the pH? And we're given that Kb is equal to that. So we're not given the chemical formula of codeine, but we don't need it because we remember that our general equation for bases was some base plus H2O goes to BH plus OH. All right, and we can fit it into this format even if we don't know the equation. So codeine is this right here. It's our starting base. So the first thing we do is we write our K expression, Kb. Kb is equal to products over reactants. So BH over OH over
Bro,
B.
what the fuck?
And I got some questions over the past couple days as to why we don't include H2O in our formula. It's because H2O is a liquid. And I might have mentioned that once a couple classes ago. It's not too important in this class, but you will learn more about it in AP Chemistry. But for the purposes of my class, just to know that H2O never goes into the K equation. So we have this K equation, and now we set up our rice box. So RICE. Now, we're given that we start with 0.05. So we're going to put 0.05 molar here because remember, it's molar already. It has to be molar before it goes in the icebox. We don't care about H2O. It's a liquid. And we start with 0 of this BH and 0 of OH because we just literally dump in some codeine. So this is all we have at the start. We're going to follow through with our change column. We're going to subtract X on this side and add X on this side. So here we get 0.05 minus X. And X on both sides later, on the right side. We're going to plug into our K equation. Kb is equal to 1.6 times 10 to the negative 6, which equals X times X over 0.05 minus X. I'm going to simplify this into X squared over 0.05 minus X equals 1.6 times 10 to the negative 6. Now, I have to solve a quadratic, it looks like. But I'm going to get rid of this X so we don't have to do that. And when we solve for X, we get X equals 2.83 times 10 to the negative 4. So I don't want to waste too much time doing it out, but that's what X equals. And if we look here at our equilibrium column, OH is equal to X. So now we can say OH is equal to 2.83 times 10 to the negative 4. And now we can find POH, which equals minus log of OH, of that number. So POH is equal to 3.55. And then once we have POH, we can find pH by doing pH plus POH is equal to 14. And we get pH is equal to 10.45. So that's the pH of a 0.05 molar solution of codeine. Well, when's the last time you heard that in Hartford, huh? All right.
More.
What's that? I wish I could get this thing to focus today. Let's see if it's dirty.
If that was with your pants, bro, I swear to God.
No, that was with the... This thing takes time to warm up anyway.
It's like when codeine hits your system.
The other yeah, this is what your vision looks like once you take codeine. Don't worry, the other instructor will have better technology than me. Sorry about all the tech.
Oh, we won't, bro. You're lying.
All right, so any questions on anything on the homework? All right, so before we start today's class, I want to go back to last class a little bit to talk about a point that I skipped over because it wasn't too important last class. I have a strong acid. And if you look on your packet last time, I gave you guys a little chart, a little list of all the strong acids and bases. So I'm going to pull one, HCl, strong acid. So HCl is so strong that every single one of HCl is going to break up into H and Cl, H plus and Cl minus. It's so strong that it literally just dumps all of the hydrogen out. It is, for lack of a better analogy, it wants to take its hat off so badly and not put it back on. So if this was a bunch of college kids, I would say it wants to take its pants off. But for the purpose of this class, it wants to take the hat off. Anyway, what we learned last time was that I said one of the rules we have is if the starting acid is strong, the CB, the conjugate base, is... Does anybody remember what the rule was? If the starting acid is strong, HCl is super strong, the conjugate base is extremely weak. Well, yes, Kevin, that's the answer. So this is HCl right here. That's our starting acid. What's our conjugate base? Anyone want to take a guess?
What'd you say?
What's the conjugate base in this reaction?
Fucking CL.
Yeah, it looks a little different than the one I wrote last time. But Cl, this is still the conjugate base. So our starting acid is super strong, and the conjugate base it produces is super weak. Now the question is why? And that's what I didn't explain last time. Anyone want to take a guess why the conjugate base is super weak? So I'm going to explain it, and if you don't understand it, it's okay. I didn't understand this even when I took the AP Chem exam, which is why it didn't go so well. But anyway, that's besides the point. The conjugate base, what it wants to do is it wants to react with the H plus and go back to HCl. It wants to do the reverse reaction, just like equilibrium. But what happens is, and I'm going to talk about the hats again, the HCl was such a strong acid, it wants to take off its hat. And it wants to leave the hat off. It wants to take the hat off so bad and produce H plus and Cl minus that why would it want to put the hat back on?
That's some like rapist shit, bro.
That's why I changed it to hats and not pants, Kevin. So HCl is such a strong acid, it takes off the hat and it doesn't want to put it back on. And that's why it's the conjugate base, Cl, is a weak acid, because it doesn't want to put the hat back on to go back to HCl. So strong acids have no equilibrium. It's just a one-way arrow. It's a one-way street. It doesn't go backwards at all. All right, are we good on that? So when you see strong acid or strong base, no equilibrium. That's the one exception we're going to talk about. So remember how I talked about equilibrium was kind of like flashing the shirt? So the strong acid, strong base is just like lifting the shirt and leaving it there. Not bringing it back down or up again. All right, today we're going to talk about titration. Who's heard of titration before? All right. Oh, welcome, Abhinav. You're just in time. We're just about to start new material. Titration is a lab technique. And this is a little tricky to understand, so I'm going to try to draw it out. You have this beaker-looking thing. This is called the flask. And you have this long cylindrical object. with fluid inside. And you also have fluid inside the flask. Two different kinds of fluids. This long cylindrical object here is called a burette. So we have two different solutions. One solution goes in the flask, and the other goes into the burette. All right? So that's the first answer to one of the blanks. It goes in the flask and the burette. The volume of the solution in the flask doesn't change. All right? But here's what happens. The burette solution gets slowly added into the flask. And a burette, you'll see it when you take chemistry lab. There's literally a little stopcock where you can open it and drip, drip, drip the solution from the burette into the flask. All right?
It's like that one like doctor like impregnated his like.
Why are you watching?
Bro, you watched it with me.
I cannot confirm or deny. Anyway, what happens is the flask and the burette, one of the liquids is an acid, one of the liquids is a base. So what happens is, as we keep dripping water from the burette into the flask, the pH changes. And this is leading into what we're going to do today. Last class, I showed you how to calculate the pH of an acid by itself and a base by itself. Today, I'm going to teach you how to calculate the pH when we mix the two together, when we mix the acid and the base together, all right? So, what we have to learn is that every time the acid and the base combine, acid and base do something to each other. They neutralize each other. And they produce water. Now, I had an analogy for this, but it's very bad, as in not child-friendly. And there are children in this call. So for the purposes of staying in college, I will not say it out loud.
Say it.
But see me after class. All right, so the formula. When we have a strong acid.
Oh, shit, I know what you're talking about.
Strong acid and a strong base. Because acid is just H plus and base is just OH. Strong acid mixes with strong base, produces H2O. All right, and today we're going to learn about how the pH changes. Just some vocab that you guys might see in AP Chemistry. This is called an indicator. Has anyone heard of an indicator in chemistry? So what happens is when we keep titrating, we get to a point that's called the equivalence point. The equivalence point, and I will put a big star next to this. The equivalence point is defined as the point in the titration where the moles of H plus equal the moles of OH minus. You have a 1-to-1 ratio. If you have 10 H pluses, you have 10 OH minuses. They are equal in amount. So what an indicator does is, let's say we're titrating something like this. We keep drip, drip, dripping the solution one into the other. How do we know when we reach the equivalence point? Well, the point of an indicator is the indicator changes color. It's a special chemical that changes color when we reach the equivalence point. So I'll put it right here. An indicator changes color at the equivalence point, which means that you keep dripping the solution in, and once you pass a certain pH, the chemical is going to change color. And that's how you know you've reached the equivalence point. Right at the moment it changes color. All right. So we use titrations to neutralize acids and bases. But the big question is, why do we care about it anyway? In theory, and you don't have to catch on to this too well, but if we have a solution that we know everything about, and we have a solution we don't know about, we can put the known solution into the flask, and we can put the known solution into the burette and titrate it with the unknown solution. And then once we get to the equivalence point, we can work backwards to find what the unknown solution was. So you don't have to understand that part too well, because Ms. Powell will definitely explain that in detail when you get to chemistry. But today I want to teach you guys how to calculate the pH. Any questions so far? All right, you guys are not going to like me by the time we finish this. All right, we're going to do strong acid, strong base, titration. So, here's our little beaker. And here's our little burette. Now, here's the thing. When we have a strong acid, strong base titration, the acid goes in the flask and the base goes in the burette. Okay? So we start with an amount of acid and we keep dripping the base into it. And every drop we add in, we produce more water. Because the formula is H plus OH goes to H2O. All right? Now, here's the very important thing. The very important thing that we're going to learn when we do this, this kind of reaction. When we do a strong acid and strong base titration, not a weak acid, not a weak base titration, but when they're both strong, if both the acid and the base are strong, we assume that the CB or the CA have no effect on the solution. Which means that the only thing that's affecting the solution is the acid and the base that we add, not the conjugates. They just float around and do nothing. They just float around and chill, just like the kings and queens of England, all right? They don't contribute anything to our reaction, all right? So now, what we have to do first before we start titrating is we have to look at a graph. And if you're like me, you hate graphs. Who likes graphs here? No one likes graphs. All right. This is a titration curve. The first thing we always do is we look at the x-axis, and then we look at the y-axis. This is volume of NaOH added. So this is the base. Or volume of base added, I should say, not NaOH. So what this means is, as we keep dripping the base into the flask, the amount of base is going to go up. And as the amount of base goes up, the pH is going to change. So on the x-axis, we have base added. On the y-axis, we have pH. As we increase the amount of base that we drip into the flask, we're going to increase the pH as it goes up. Now, there are a couple regions on this graph I want you to know. See this flat region right here? This is called the before equivalence point. This part right here, where it shoots straight up, this is the equivalence point. And that's the point where the amount of H equals the amount of OH. Finally, we have this flat-looking thing up here. This is called after the equilibrium point. And what that basically means is we keep adding, and we finally get to a point where the amount of H equals OH. It is perfect. The indicator changed color to let us know, but then our dumbass just overshoots it, and we keep overshooting, and then now it's not equal anymore. And what you have to do when you do that is you stay after during lunch and do the whole experiment again, because that's exactly what happened to me and my group, because my partner was that's another story. Never mind. Anyway, any questions on that? All right, so first I'm going to show you guys how to do the calculation before the equivalence point. So I'm going to show you how to calculate the pH when we're in this region of the graph, this first region right here. All right, what happens is, before the equivalence point, we're adding base into the acid, and as soon as the drop of base hits the acid, it forms water immediately. But would you guys agree with me that, let's say we just started, the first drop of base we add in, would you agree there's more acid than base? So the base runs out first, right? Because even after that one drop gets converted to water, there's still lots of acid left over, but there's no more base because we only added one drop. So what happens is, before the equivalence point, the base, also known as the OH, runs out first. And we're going to see what that means right now. So when I say it runs out, it gets completely neutralized. All right, so let's do an example. Example 1. So we're right here. So you have 0.025 liters of 1.1 molar HCl. Is that the acid or the base?
Acid.
Acid, right. How do we know? Because it has an H, right? Now we have the NaOH, that's the base. So just to sketch it out, this is what it looks like. In the beaker, we have the HCl, the acid. And then we're slowly adding the NaOH, which is in the burette. We're going drop by drop by drop. Find the pH. Oh, shit. Great. Now, I hated these problems when I first learned this, but I'm going to try to show you guys how to do it step by step. If at any point anyone gets lost, please ask me to slow down. Step 1. And I tried to write out the steps on the side for you guys, but I'm not sure how clear my writing is, because you can never tell if something's clear to you but clear to someone else. All right. Step 1 is to find the moles of H and OH. Always find that first. So let's start with the acid. Let's start with the H. So we have 0.25025 liters of HCl, and we're given a molarity. So we can use that as our conversion factor, because in 1 liter, there's 0.1 moles of HCl. Now we got to moles of HCl. And for every 1 mole of HCl, we have 1 H+. So when you put that in our calculator, we get 0.0025 moles of H+. Any questions on that? Now we do the same for OH. We start with 0.0125 liters of NaOH, which is a strong base. We're given a molarity, so we're going to use that to convert it to moles of NaOH. And in every 1 NaOH, we have 1 mole of H+. OH. So when you put that in the calculator, we get 0.00125 moles of base OH. Any questions on how I got that? Step 2. All right. Do we need a second to copy it down? All right. I know I did that fast. Don't be like me, okay? Don't be the kid that got lost and doesn't say anything, okay? Please let me know if you need me to repeat. Step 2. If we look on our instructions, step 2 says, set up the mole ice box. This is the mole rice box. Now, this is where things get weird. Do you remember how last time, or a couple of times ago, I said you can only plug molarity into an icebox? Well, this, you're not going to like me for this. This is the one exception. This is a different kind of rice box than the one we did last time. It's called a mole ice. I call it the mole ice box. You're not going to see it on the textbook, but I like to call it that so I can distinguish between the other ice box. But this is the mole rice box where we are going to plug moles in. So keep these two separate in your mind. It's a totally different kind of rice box, okay? So we're going to use the formula. Let me just write rice on the side, Rice University. We're going to use the formula H plus OH goes to H2O. And I'm going to plug in the starting amounts of H and OH that we just calculated. So we started with 0.0025 moles of H and 0.00125 moles of base. Now, normally when we do a rice box, what goes in the change column? Does anyone remember?
The X's.
The X's, right? That's for regular ice boxes. For this rice box, it's different, okay? What we're gonna do is we're gonna look at these two numbers, the starting concentrations, and we're gonna find the one that's smaller. What's the smallest thing here? And I'm not talking about ROM this time. What's the smallest thing here?
0.00125 for that OH.
0.00125, yep. So there's less base, right? Good. Whichever thing is smaller runs to 0. It goes to 0. So we're going to subtract the smallest thing from both sides. Which, I'm going to let you guys write it down before I go on. Which makes sense, right? Because if we look at our picture, we're adding small drops of NaOH, of base, into the acid. So as soon as that drop hits the surface of the acid, it runs out. It goes to 0. So that's exactly what we're doing here. That's why we're letting the smaller thing go to 0. So this minus this goes to 0, right? And this side, we have to plug it into our calculator. And we get 0.00125. All right. So that's the amount of acid left over after it has been neutralized by the base. So I'm going to say acid left over after the base neutralized it. And remember, neutralize just means convert it to water. So we added acid to base, and it produced water. All right, are we good? Now, step 3. Step 3 is to take the thing that's left over and define the new concentration. So we added base to the acid, right? And the acid killed all the base. But now there's still acid left over, so we have to find the new concentration of the acid. So what we're going to do is we're going to take the amount of acid we have left, moles of H, because this icebox gave us moles because we put moles into it. And we're going to divide it by the total volume to get a molarity, because molarity is moles divided by liter. I'm going to write down the side. Molarity equals moles divided by liters. So we have moles up top. Now we just have to divide by liters. Here's the thing, though. Would you guys agree that as we keep adding drops of base into the liquid, the volume inside the beaker is going to go up? So we have to account for that. To find the total liters, we have to add the amount of acid we started with and the amount of base that we added into it. So we started with 0.025 liters of acid, and we're adding on how much base we added in. So if I put this into my calculator, I'm getting the molarity of hydrogen is equal to 0.033. Any questions so far? So step 4. Our goal was to find pH, right? Well, we're close, because we just found the concentration of hydrogen at the end of the reaction. So now step 4 is to just plug in to the formula. Remember, pH equals minus log of the hydrogen concentration. So we literally just do pH equals minus log of 0.033, which is the concentration we just found. And when I put that into the calculator, I get pH is equal to 1.477. That is our final answer. Any questions? Anything I need to repeat? I'll lay them side by side in case you guys need to copy anything. Oh well, I can't really side by side it. I'll go up and down slowly. We good? All right, so that was how you find the pH at this region. Now, let's say we keep adding base. And you see how for a long time, as we keep adding base, we still stick within this region? But then all of a sudden it shoots up. And then now we're into this region, the green region, where we're at the equivalence point. Once we get to the equivalence point, there's a separate set of steps on how we find the pH. So if we flip the, oh, actually it's on the bottom of the page, equivalence point steps. At the equivalence point, which is right here. So this is the series of steps you use when you're right here. So, someone remind me again, what's the definition of an equivalence point?
The point at which the hydrogen and the base and the acid are equal.
Exactly, yes. At the equivalence point, the moles of H equals the moles of OH. All right? And I'll say that the indicator changes color. Yeah, Michael Jackson. Oh, wait, no, I'm sorry. Nope. I didn't say it.
Yeah,
all right.
The skin condition.
Okay, Kevin, that's another topic.
Skin.
Ask Sanfik. That's bio. That's bio. So if the moles of H equals the moles of OH at the equivalence point, what happens is they run out at the same time. Which makes sense, right? If you're eating your if you eat your rice at the same rate that you're eating your curry, your vegetables, they run out at the same time.
Why'd you switch to curry for vegetables?
That's just the first thing that came to my mind. Because like it was a good like because like you have to mix the two together or whatever. Anyway, so the moles of H and the moles of OH run out at the same time. Okay, so there's no acid and no base left over because they just kill each other off, and all we're left with is water. So here's the rule: in a strong acid, strong base titration, if you get to a point where you find the moles of the H equals mole of OH, and you know you're at the equivalence point, the pH always equals 7. So just remember, if you're at the equivalence point, the pH is always 7. And I'll show you how to do the example on the next page. You have 0.025 liters of 0.1 molar HCl, and you add a total amount of 0.025 liters of 0.1 molar NaOH. So it's the first problem on the next page, problem B, at equivalence point. So we have our base here. Oh, sorry, this is our acid. And we added in base. We kept adding to the point where we added a total of this much, and we're at the equivalence point. So the first step is to find the moles of each thing. So let's start with the hydrogen first. Start with that many liters, and we're given a molarity. So 1 liter is equal to 0.1 moles of HCl. And for every 1 HCl, we have 1 hydrogen. And that gives us 0.0025 moles of H+. Now for the OH, we start with 0.025 liters of NaOH, and we multiply it by 1 liter, or divide by 1 liter, and use the molarity. And for every 1 NaOH, there's 1 OH. That gives us 0.0025 moles of OH. So first step, we found the moles of each thing. You see how they're equal? You see how they're equal? pH equals 7. Don't even have to think about it. You just stamp it across your work. Any questions? And you might be wondering, why is it 7? Why is it not 13 or 20? Because when the acid and the base equal each other, they kill each other off and produce water. So the only thing floating around in the beaker now is water, and the pH of water is 7. That's why. Anybody need me to repeat anything? All right. The last thing for today. So we started off with just acid. We kept adding base. And then we kept adding base. And then we reached the equivalence point. We were good. The indicator changed color. We were clearly there. And then our dumbass was on our phone. So now we overshoot it. We add too much base. Uh-oh, and we're not at the equivalence point anymore. because we were watching porn on our phone when we should have been monitoring the flask. So now we just ruined our titration and we overshot it. But we can still find the pH, which is what I'm going to show you guys now. So this is what happens when we're after the equivalence point. We passed it already. Or maybe we weren't on our phone. Maybe we're just colorblind. All right, so I'm looking at the next page after the equivalence point. Just give you guys a quick chance to finish any stray notes while I'm redrawing this. So, what this looks like visually, we keep adding base into our acid. We keep adding it and keep adding it and keep adding it to the point where they're equal. But then once we're equal and we overshoot it because we were on our phone instead of paying attention, everything, all the acid goes away. So there's no more acid left. But we just keep adding base and keep adding base and keep adding base. So we're filling up with base. So what happens is H plus OH goes to H2O. The H runs out first now. Acid runs out first. So now the only thing left in the beaker is base and water. Because there's no more acid to neutralize it. So, let me show you guys how to do the problem. Any questions so far? Now, all right, so this is the last example here. We have this much acid, and we add this much base. The first step is to always find the moles of starting H and OH. It's the same thing as before. So, I want to give you guys a chance to engage a little bit. So how about this? All of the boys, why don't you guys find the moles of H for us? And all of the girls, let's find the moles of OH to start with.
I identify as non-binary.
Then you know what? You get to find both. Yay! Extra work. Well, you thought it was going to be easy, like which bathroom door do I go through? Nah, you get to find both, because you can use both bathrooms, so now you can do both problems.
You're homophobic.
This is chemistry. It has nothing to do with that.
Homophobia is a huge problem.
You can talk about this with Gotham.
How do I do this?
It's on the last example. So you start with the amount you're given, and then we're going to use the molarity to convert it to moles.
That's too hard. I can't do it.
Yes, you can. If you ever get to a point where you're like, I can't do this. Yes, you can. Because I'm the dumbest one here. And even my dumbass can do it. So you guys are going to be rock stars. You guys can do this.
I don't want to be a rock star. I want to be a porn star.
If that's the case, there's a totally separate class you should be in right now.
What is that?
See me after class. All right, look up when you're done. All right, who found the H's? The boys? All right, shout it out. What did we get for moles of H?
0.0025 moles.
Yep, so I'm going to do it really quick just to check us. So we start with this amount of HCl. We use the molarity. It's 1 HCl and 1 H equals 0.0025 moles of H. All right, good job. Girls, what did we get for the OH?
I got 0.00375 moles.
0.00, all right. Do we agree, disagree? Anybody?
Yeah, that's right.
That's right? All right, let me see. One OH. 375 moles of OH. Correct. Yep. All right. So now, we're good with step one? And our non-binaries, did we get the same answer?
Yeah.
Okay, thank you.
Ow.
I should have had him read both of them, actually. All right, that was step one. Step two is to use the mole icebox. It's the same thing as before. Same thing as when we were before the equivalence point. So RICE, H plus OH goes to H2O. We're going to plug in what we start with. So we start with 0.0025 moles of acid, 0.00375 moles of base. What's going to run out first? Which one is smaller?
The 0.0025.
Yep. So which runs out first, the acid or the base?
The left one.
The acid, yep. So we're going to let that one go to 0. So we're going to subtract 0.0025 from both sides. So that goes to 0. And when I put this in the calculator, I get 0.00125 moles of OH. Is that right? I think so.
No, wait. Is that a 7.5?
2.5.
No, I mean like the 0.00375.
Yes, yeah, that's a 7.
It's 0.0015. Oh, is it not?
Is it 7? Girl, what did the girls get? It was 3.75, right?
Yeah.
Oh, okay. Thank you. See, non-binary, they were right.
What did I do? Wait, what did I do?
It's 0.00375.
Oh, okay.
All right, I'll even fix it. There we go. All right, so now.
Justin, I'm sorry. It's just the mental health. It's like the.
Step 3. There's no acid left, but there's base left. So now we have to find the concentration of the base of the OH. So we ended with 0.00125 moles of OH. And we remember that concentration, molarity, equals moles over liters. So we have to divide this number of moles by liters. So we look up here, and we see the volumes that we combined of the acid and the base. So we're going to add those two again. So 0.025 liters plus 0.0375 liters. And I'll put this in the calculator. Oh, shoot, I messed the calculator up. I'm getting OH is equal to about 0.02 molar. Does that sound about right? Good so far? All right, step 4. We have an OH, right? So we can find the POH. So POH is equal to minus log OH. So POH is equal to minus log 0.02 molar. And when I put that in the calculator, I get POH is equal to 1.699 or something. But we don't want POH, we want pH. So finally, step 5 is once we have POH, we're going to find pH. So pH plus POH equal to 14. And we know that this is 1.69. So pH is equal to 12.3. That's our final answer. Any questions whatsoever? Anything you guys want me to repeat? Good teamwork. We worked together and we solved the problem.
Still mad at you for not accepting my identity.
Hey, nothing saying I didn't accept it. I just made you do it twice.
You don't know if I have a dick or not.
All right, so there was something I wanted to go over to prep for next class, but I think we covered a lot today. I'm going to save it for next class. It was the very last page on this sheet. It said preparation for next class. I'll go over it next class, or maybe I'll make a video to go over it. Or maybe I'll probably just go over it at the start of next class. But that was the lecture for today. So let's go to the worksheet. All right. You guys are not going to like me when I show you this. This is the worksheet. I'm trying to get a full body view of this, but anyway, this is the worksheet. And hold your breath. This is the homework. So I see the jaws dropping now. I see the jaws dropping. So now here's the thing. With titration, this takes a lot of practice. So you see how there was a lot of math, and if we messed up one little number, it messes up our whole calculation? The key is to practice. Practice as much as you can with this. And if you do practice, do upload it onto the classroom so I know not to put your name on the list. But I'm asking that try to review your work. Try to review the problems I went over first. Get a good grip of those, then try the problems and check the answers for the worksheet if you got them right or not. But other than that, we'll go into our worksheet section now. I'll be here. I'll start an extension link in case you guys are working and you have questions. You can come back. But you guys are free to start working on the worksheet. And just a quick temperature check. Somebody, or as many of you, unmute and tell me, how bad was this lesson? This is one of the more tricky topics. Was it easier or harder than last 2 classes? About the same? All right. Nobody cried yet, right? I mean, I can only see the people with the cameras on. But
I cried
next,
when you made me do 2 times the work because I'm gender neutral.
I don't know if you're crying because of that or because of my chem class, but next class is going to be, I've seen people cry for next class. It happened in AP chemistry. You know, half the class falls behind before you know someone busts into tears. So I'm going to try to make next class as little painful as possible, but next class is going to be bad. But I do recommend coming just so you see it before going to chem. Even if you don't understand it all, it's good to see it once. All right. Looks like the meeting is going to kick me out. I'll send an extension link in case you guys have more questions or want to work through the problems. And all right, I'll just let it run out, and then I'll start a new one. Thanks for coming today. I hope you learned something.
Fuck you. I'm gonna go play on my dick. By the way, guys, I'm not gender neutral. I'm a functioning male in society.